the way I titled this is Differential Equations in 2021 because basically what it's saying is where do we plan on being with differential equation solvers and the differential equation kind of ecosystem around it in the year 2021, right? So what are all these ideas that are being incorporated, and what are the problems that are trying to be solved? Um, so yeah, as I said, I have multiple positions here. So applied mathematics instructor at MIT, senior research analyst in the School of Pharmacy at the University of Maryland, and then also the director of scientific research at Boomis AI. So I have a set of things where I'm doing in pharmaceutical modeling and simulation, also just the mathematics department at MIT. It sounds like it's a disconnect, but actually all of it is differential equations under the hood. So um, just a lot of differential equations. So the place I like to start here on, especially on scientific machine learning, is just by starting at the universal approximation theorem, right? So this sounds a little bit weird, but I'll be getting to where this connection really comes in. And the idea is that a neural network can get epsilon close to any Rn to Rm function, right? So like if you have a neural network, it really is if you make that neural network big enough, it can be an approximator to any possible nonlinear function if you just choose the right parameters, right? So in some sense, a neural network is a way to be able to represent any possible function in a form that is just a discrete set of parameters that need to be found. So it's kind of like a Taylor series in some sense, if you think about it like that. It is very good for computing though, because everything is just nice matrix multiplications. It's just really bad for analysis because there's not a single parameter in there that you necessarily know analytically. Everything has to be done through optimization, but the computation is very well suited for GPUs and it's very quite stable. And there's a lot of nice properties like how, there's a bunch of local minima, but all those local minima are actually very close to the global optima. So you might as well just do local optimization. So it has a lot of nice properties where if you just kind of do gradient descent on it, you tend to find the similar or the same Rn to Rm function, even if the parameters are different all the time. So they have some very magical properties, and they also work very, very well in high dimensions. So they are this approximator for missing functions, and this is the key object that we'll be using in a lot of new aspects of differential equations throughout this talk. And so the idea here is that universal differential equations are differential equations defined in part by universal approximators. That means that they use all scientific features, right? So all the numerical methods that you have, and then you kind of cover the last mile of the approximation of the modeling sequence and everything with the neural network embedded within your model. So to demonstrate how that works, I like to use this toy model. So there's this toy model of COVID-19 outbreak, right, which is kind of this extended SEIR model with a key term, beta term that was found. So this is a direct model where this beta term models the exposure, which is the amount of exposure to COVID-19, which could be highly variable across country to country. And so what we're going to do is we're going to use data from this model and see if we can automatically recover this model. And what are the ways to automatically learn such a model? With the differential equation solving. And the first thing that you can do is you can say, well, a neural network is an arbitrary function approximator, right? So if you want to learn what the ODE is that you're solving directly from the data set, then you can just say U prime equals neural network, right? If you can put that neural network inside of the differential equation solver, which is something that we'll be describing a little bit later, exactly how the training is done, we can just kind of willy-nilly embed neural networks inside the differential equation solver. Then you can say U prime equals some function. You want to learn that function. And so you just replace it with the neural network. And what you'll get from that is you'll kind of learn something. You'll learn something that is kind of representative of the dynamics in the training data. So here I train it from 0 to 21 days. And then I extrapolate out from that, and I ask the question: how well has it actually learned the dynamical system? And it hasn't done too well, right? So this is kind of what you see from standard machine learning, right? That it understands what it learns from the data, but doesn't have enough information to be able to, extrapolate from where it does. So that's why a lot of people make use of a lot of mechanistic modeling as well. And so then we start to ask the question, what happens if you start to mix this with mechanistic modeling? So now here is a version of the SEIR model where we say, well, we know quite a lot about SEIR, right? We know a lot about COVID-19, right? So for example, if someone is infected, we know the rate at which they recover. We know the amount of days that it takes for them to, um, well, we know the percentage of them that go to the hospital versus not, right? So, people who have the infection but are not hospitalized. D are the percentage of people who are hospitalized. And so there's a rate constant in there that is for the percentage that is hospitalized. And then there's a constant in there for the rate at which the recovery occurs. So um, s- so a lot of the terms in the SEIR model can be quite well known, right? Because we know it takes like 5 to 7 days for COVID-19 a recovery to occur. We know the percentage of people that end up being hospitalized. So what we can do is you can write down a mechanistic model that captures most of the idea. But the thing that we don't actually know about is the exposure, right? So the exposure is something that's highly variable depending on um, whether it's dependent on things like whether people are following quarantine rules. It's dependent on um, whether people are wearing masks, right? So what we don't really know is whether what the exposure term would be inside of this model. And so what we do is we just say this is an unknown function. We can have a neural network that takes in some quantities and spits out a value here. It's minus that value here plus that value here, and now we have a model which is, this neural network embedded within a mechanistic model. And what we do is we train this, and it will learn. So this is actually a plot here of what the estimated versus true exposure is. What it will do is the neural network will learn to be the missing exposure term in this model, and then it'll perform quite well in this extrapolation, right? So has this behavior where we train it from 0 to 21 days, and up till about like day 40, it's actually giving you a pretty good estimation because it has bits of that mechanistic model. It has a lot of that scientific knowledge, but it is truly learning what that background exposure term is. Um, but it's not getting everything correct yet, so we need one last piece in there. What is that piece? Well, so there's this method that people know about, which is the SIND, which is sparse identification of dynamical systems. And the idea here is that you can build a dictionary. You can choose a dictionary like all polynomials plus all trigonometric terms. And if you evaluate every single time point of your data on this dictionary, you can build a linear system and do a sparse regression, and that will recover what the basis elements or what the coefficients are in the basis of elements that you've chosen to be able to get a symbolic representation of data. Another way of saying that is you can recover a symbolic version of your dynamical system directly from data, and so you can like identify what the dynamical system should have been just by looking at a time series. Now, while that can work in practice if you have enough data, if you just directly apply this to the system we're looking at here, you get a huge number times cosine of u1 plus cosine. You get a system which is essentially unidentified, and the reason is because it doesn't have enough information to really understand the whole function, right? There's not enough data to be able to give you back this whole dynamical system. But could we use this idea of sparse identification and getting back to mechanistic equations directly with the neural network approach? Yes, we can. So what we can do is we can take input-output pairs of this neural network. We can do the sparse regression or symbolic regression to return um, a polynomial form or trigonometric form of the neural network. And what you can do is you can say, well, here is this unknown function. I train the neural network. I then do a symbolic regression, and then the best approximating symbolic regression here is this polynomial which I show at the top. Now this ends up being a lot more stable than doing an approach of just putting a bunch of random terms in the differential equation, being like a really quick way to be able to find a missing function and turn that function into the best approximating symbolic form. And what comes out of this is two things, right? The first thing is that it says that the exposure term is not actually dependent on the percentage of people who went to the hospital, even though it was allowed to be, which makes sense because people who are hospitalized are generally not part of the exposure process, right? Because they're kind of isolated. And the other thing here is that you see that it fixes our extrapolation problem because it's actually learned a fairly correct model of the process. And so even though we only train this from 0 to 21 days, we put a neural network on there, we find what the missing mechanistic terms are, we extrapolate out to 60 days, and you're able to see that it works fairly well. Right? It's not perfect, but it's very good. So this is the idea that's going on with this universal differential equation modeling, where we're using neural networks as steps within this process of model identification and discovery of missing terms, and in the quantification of epistemic model uncertainty. Right. So the general idea here is this, just to recap, this is this ML augmented scientific modeling approach where what we do is we identify the known parts of the model. We train neural networks within the unknown parts of the model. We sparse identify this back to mechanistic terms. We verify that these terms are scientifically plausible. We extrapolate from data, and we get more data to verify the terms, right? Like, for example, now that we have made an approximation and we say that certain processes are involved, certain processes are not involved, the relationship is quadratic, we can go back and we can double check the mechanistic model, right? We can build experiments to be able to say, yes, this term that we have added to the equations makes sense. And so the idea here is that we can use all of these advanced numerical methods that we've developed in scientific computing, along with these data-driven machine learning methods, to be able to do this automated model discovery. And this isn't just one example that's worked out. There's a lot of these examples that have very surprising behaviors. So here is Lockville-Terry equations, where the truth equation is, the Lockville-Terry equations that you know and love, just a quadratic polynomial. Um, the embedded equations, what we do is we say that we know the linear terms of the Lockville-Terry equation, which is just the amount of rabbits grows exponentially, the amount of wolves dies off, and then we just say there's neural networks added to that. We train it on data from 0 to 3 days, which is just the amount of wolves is dying off, the amount of rabbits is going up. We say take what you've learned and extrapolate, and then when we extrapolate this, it sees that there's going to be cyclic behavior in the future, right? So there is no cycle in the training data, but it's able to capture and learn from this training data that the way that you can represent, the way that this dynamical system should be existing, given what we see in the 0 to 3 days, should be something that is cyclic in the future, and it matches the cycle, matches the periodicity and all that, because it's found a sparse form. Right. So there's a lot of different models, a lot of different dynamical behaviors that this is then able to capture even from very small amounts of data. So a way to think about this kind of is, you need a fixed amount of knowledge to be able to get a full recovery and a full discovery of the system. And what we're doing here is we're kind of supplementing data, right? Knowledge from data with knowledge from models. And if we put the two together, we can like hit that threshold for the right amount of data to be able to do a correct estimation, even if we don't have a data set that has all the information, all the features that we would have needed, right? And so we're starting to make use of this in a lot more applications. So this is an application, the CMU that we've been working on, and what's happening here is that they started with this uh, battery model, that is a state-of-the-art battery model, and then they made use of universal differential equation approach. So they put these neural networks in areas that are known to have the most questions or the most uncertainty, and they fit this against some data. And then what they were able to find was they were able to build a model that predicts the properties of new battery materials, and it predicts their degradation by about 19% better than the state-of-the-art model, right? So this is a very interesting application that I like because this is one of those cases where the field of battery modeling, if you increase the training accuracy by, or if you increase the prediction by 3%, 5%, that's considered fairly significant because these models are fairly sophisticated and they're fairly accurate already. But what this is doing is saying, what happens if we start with the most state-of-the-art model, and then what we ask is we ask the question of what can machine learning add to this, right? So you take a full mechanistic model of these batteries, and then you add specific neural networks and the pieces that are going to have the most uncertainty, and then you use that to be able to augment the model and kind of guide it and figure out what these missing this model should be extended, in the next few years of physical research, and then that gives you something that really is able to account for the terms that haven't been discovered yet. So, why is this able to do so much better than the state of the art? Well, because the worst it could do is the state of the art, because that's where it starts from, right? And that's kind of like a nice property of this application or this form of scientific machine learning. But ODEs are simple. Everyone wants to move to more difficult equations. So what are the more, and how do you start to bring this to larger applications and more difficult approximations? So what we've been able to show is, in one case here, we have the differential algebraic equations. And what you can do is you can say, here I have a model where I don't know some of the terms of the model, so let's put neural networks in there. But I do know that there's a conservation law, right? So this is a model of chemical kinetics. So I have one I have the concentration of the protein in 3 different forms, and so I always had to have 100% of the protein. So let's make sure that I have y1 plus y2 plus y3 equals 1 at all times. But now I have a dynamical system of y1 and y2 defined by neural networks. Y3 is implicitly given by the conservation law. Let's learn what the dynamics in this case should be, and we treat this as a mass matrix DAE, and we're able to do the same process, and we're able to learn what the missing model is, where what we're using is we're using some information about the model, and we're using some information about known conservation laws, and then we're able to rediscover what the missing chemical reactions are from this kind of information, plus a little bit of data. Now, we also are making use of discretized PDE operators and noting their relationship to convolutions. So essentially, if you look at a convolutional neural network, their core operation is this convolution, which is really taking like a subsquare of pieces, multiplying it by coefficients, and then that's how it calculates the result, right? So this is a convolution, which you can see the red numbers for what the coefficients are going to be, and it runs that at each square, and then multiplies the numbers in the boxes by the coefficients, and that's how it calculates the next term of the convol feature, right? This is actually equivalent to PDE stencils. So if you take, for example, the second order finite difference, the discretization Laplacian, this is a stencil which is 1, 1, 1 minus 4 is the coefficients. And you just take that block and you multiply that to each square, right? So what we can do is we can say, well, we can use these convolutional layers or convolutional neural networks to be able to capture PDE terms, and we can mix this with neural networks inside of discretized differential equations to be able to recover the partial differential equations as well. And so this is an example of that, where what we can say is that, here is a semi-linear partial differential equation. We model the nonlinear term by a neural network. We model the derivative terms by convolutional neural networks. And by training the convolutional neural network, you can learn things like, well, the weights of the left and the right portion are equal, and the weights all sum to 1, which means that this is a constant times 1 minus 2, 1. And so what this has learned to do is it's learned to be a diffusion term. And what this reaction term has learned to do after you do the sparse identification is it has learned to do to become a nonlinear term. And so this form, where you say I have a differential equation over a large system, where I have a neural network plus a convolutional neural network, after training, you can reinterpret this and realize that what is discovered is that your spatiotemporal model is a semi-linear diffusion equation with a quadratic reaction, right? So you're able to kind of rediscover this full partial differential equation directly from this specific mixture of a neural network and a convolutional neural network, because of this property, this relationship of convolutions to discretizations. So that's all about physical model discovery. So if you don't know what your physical equations should be, and like we have a lot of pharmacology, this is one way to be able to discover a lot of these missing terms. But neural networks can also be used in scientific simulation to accelerate these simulators themselves. So a very interesting project that we're doing with the climate climate model being co-developed between MIT and Caltech. And one of the cores to the climate model is that the ocean model is that in each voxel of the ocean, you need to solve the Boston-esque equations. Boston-esque approximated Navier-Stokes equations, which is this 3D partial differential equation here. But at each part in the ocean, all that you really need for this climate model is you need a one-dimensional model of what the heat is in the ocean column as you go down up and down that column. And what we can do there is we can say, well, let's take an XY average throughout the Navier-Stokes equations. So you take an integral of this equation, and then if you do that, you can get a one-dimensional partial differential equation, which is the approximate to the 3D equations. But you can't actually close this equation. So you get a one-dimensional PDE, but you get infinitely many one-dimensional PDEs that are required to be solved in order to get this equation. But we can do a closure here where we say, well, we chop off all the other equations and we get a diffusion advection term where we don't know what this function would be because it's defined by its own one-to partial differential equation. That's this recursion of closure terms. And so we have a partial differential equation where we have an unknown function, but if we know this function, then we have an equation that gives us a 1D approximation to the original 3D PDE. And what we can do here is we can say, well, we have a missing function embedded within a partial differential equation. Let's replace this with a neural network, find what that missing non-local function is with a neural network, and then when we do that, we are able to really accurately approximate this behavior of one dimension of the Boston-esque equations, and be able to extrapolate forward and do a lot of things. There's a paper that we just put out on this specifically that goes a bit further than the UDE paper. Um, and what it really does is it gives us a accurate approximation form which still has the physical parameters associated with inside of it. So you can say like, oh, let's look at different parts of the ocean. You change physical parameters of the Navier-Stokes model. There's direct ways to be able to change that within the this approximation. But this approximation is 15,000 times faster because it is solving a diffusion advection equation instead of a full 3D Navier-Stokes. Right, so it's really changing the computational complexity of the problem in a large way, just by learning an approximation that is the one-dimensional average of the 3D equations. Another interesting case of this is solving thousand-dimensional partial differential equations. So, usually you think about PDEs as one-dimensional, two-dimensional, three-dimensional, but you can get up to thousand-dimensional PDEs if you look at partial differential equations that are where their dimensionality is determined by probabilistic quantities. So here we have a semi-linear parabolic form where if you think about this as like the Black-Scholes equations or nonlinear Black-Scholes equations, the number of dimensions in this equation is the number of terms that you have in your portfolio. So it's not unreasonable to have a thousand-dimensional partial differential equation here, because that would just mean that you have 1,000 terms that you're tracking, or 1,000, financial assets that you're trying to optimize over. And what you can do is analytically, you can transform this parabolic partial differential equation into a backwards stochastic differential equation. And the theory says that there's some terminating equation which will be satisfied such that these two equations are equal. And the only issue here is that you don't necessarily know analytically what this term will be, because it says there exists a function such that these two terms are equal, and these two terms are, g of xt equals this u term squared, right? So there is this there's this analytical relationship which is kind of ill-defined, because analysis always just says there exists a function that, right? But we can use that there exists a function by saying, well, there's a missing function in this resulting equation. And so you can rewrite this analytical form as neural network there's missing functions within the stochastic differential equation, and you need to have that this condition is true because the analysis says that g of xt equals is this u of x is w term, right? So you can write down that my loss function is that this must be zero if I analytically have found the correct equation. Here are the missing terms in a stochastic differential equation that will give me something that is equal to the original PDE approximation. So if I find these neural networks, then if I find neural networks embedded within the stochastic differential equation, then I have an approximation to the solution to this PDE by the backwards stochastic differential equation literature. And so what this means is that we can learn neural networks inside of a 1,000 dimensional SDE, and the resulting trained neural networks directly give us a solution of this 100 or 1,000 dimensional parabolic partial differential equation. And so, there are some ways that people have seen how to do this with recurrent neural networks, but looking at this like a universal differential equation gives a gives a much broader theory for how this all occurs. So, for example, if we do this in the stochastic differential equation form, if we do a Euler-Maruyama discretization of the stochastic differential equation, you actually recover what the state-of-the-art method is in the literature for this approach. Right? It actually gives you the same exact thing as the recurrent neural network that was used to first solve the 1,000-dimensional differential equation here. But since you have this as a stochastic differential equation, you can use high order implicit adaptive SDE solvers and solve this in minutes and now actually seconds, and train the neural networks in here because you are doing more than just the Euler method, right? So this is a very powerful representation of of something that you kind of wanted to get many different data driven forms out of. So, where are we starting to go with this as like a numerical ecosystem or numerical method? Well, the problem is that ill-conditioned gradients tend to cause a lot of difficulties in scientific machine learning, and so where we as a scientific as a numerical group have been coming in is we've been developing a lot of these new methods and new techniques that kind of get around these gradient pathologies that you see in other form. So there's another form of this which is trying to approximate the entire set of differential equations, but at the solution level by a neural network. This is called the physics norm neural network. And it shows that if you have stiffness, you cannot really recover the equations well because you have these gradient pathologies in the training process. But in what I've shown here, we've shown like a lot of partial differential equations and differential algebraic equations that have stiff forms, and these forms have been able to work just well with the way that we're using the scientific machine learning. So we've been able to get around these gradient pathologies by using different architectures, and we're able to work around them with this scientific machine learning ecosystem that we built. And so the core here has really been this diffie flux, which is able to handle these stiff, ill-conditioned scientific problems. And it's able to use neural networks within, ROC methods, implicit methods for ODEs, SDEs, DAEs, delay differential equations, multi-step methods. It has around 300 different differential equation solvers, which are all able to be used to be able to handle these automated model discovery problems. And so it kind of changes the ground here, right? Because normally people, if you do if you do model discovery in some sense with machine learning, some people have done like Runge-Kutta methods, RK4 with it before, and then most people in the scientific computing community will look at this as kind of toy methods, right? Because they can't handle stiffness. But what we've really cracked is we've cracked this ability to handle stiffness and hybrid equations and differential algebraic equations directly from in this automated process with a software that is out there for people to readily use. And the implementations are very optimized. So if you get there's a differential equations library in PyTorch, which has just non-stiff differential equation solvers like a adaptive Runge-Kutta method. If you look at what the difference is in training neural networks embedded into ordinary differential equations, the new library that we have here on their example problem, the problem that they optimize in their benchmarks, we were able to solve this in 12 seconds while their library is training in 300 seconds, right? So it's orders of magnitude faster while being able to handle all these features like stiffness and partial differential equations and everything. And so this has actually become the go-to library that people are looking at when they're doing when they're doing research in the training of neural differential equations in this whole field, right? So I'm just pointing out one given example here of people looking at the different ways of doing adjoint sensitivity analysis using the terms built in the library. So we have 7 different ways of automatically generating adjoints for equations, and I'll describe a little bit of that in a second. But really, what I wanted to point out here is that diffqflux is this library that is out there, that is kind of like the basis of what people are now using for this automated discovery process when the equations are big, when they have a lot of computational expense, and when you have a lot of stiffness to them. And kind of the core idea is that universal differential equations, what we're seeing is that they're kind of like a BLOS or LAPACK of scientific machine learning, right? So you can relate a lot of different methods that people have been coming up with back to being a neural network within a differential equation. And most of what people have been doing in machine learning, you can write down as just a discretization, a fixed time step discretization of that differential equation. So neural networks or recurrent neural networks are the fixed time step Euler discretization of neural networks embedded within an ordinary differential equation. Um, Stochastic recurrent neural networks are just the Euler-Maruyama method applied to a stochastic differential equation defined by a neural network. And you can write down a lot of these, LSTMs and everything as neural networks inside of differential equations. And so not only do you get direct expansions of all these machine learning tools, but you also get the forms which are, viable for stiffness, for, time scale differences. You get extensions that allow for having, differential algebraic forms. So, encoding these physical laws inside of them. All of these extensions kind of come for free by understanding it as this larger group of universal differential equations and the scientific machine learning around handling a universal differential equation. And so what we've really done is we've kind of consolidated the training of a lot of these different model forms to be all about training universal differential equations and doing it efficiently. So how do we actually get this library that can handle, hundreds of differential equation solvers and all these different equation forms? Well, the way that we got there was we built this scientific machine learning organization with automatic composability between these libraries. So there's more than 50 libraries inside of the SciML open source organization, so I can't fit them all on a slide. But some of the key ones that interest a lot of people here are the differential equations.jl, which is the underlying high performance differential equation solvers. There's diffqflux, which allows for this, which showcases this training of neural networks and other terms embedded within there. It adds in a lot of the sensitivity analysis. So forward mode and adjoint sensitivity analysis is automated in a way. I'll give an extra slide, which is how it's going beyond kind of the previous methods for doing this. Modeling toolkit allows for symbolic numeric optimizations. So what you think of as Modelica is something that automatically on numerical code. So you can do, for example, you can give us a numerical code, and we can do automated reduction of the numerical index by changing your code directly by using this symbolic this semi-symbolic library. I'm not going to define modeling toolkit in full, but if you're interested in that, just please ask questions because there's a lot that's coming out on that recently. It's kind of like an extended Modelica. Um, we have neural PDE.jl, which is automated physics informed neural networks and deep BSD methods. So for high dimensional partial differential equations and for integral differential equations, it's a library that you write down the symbolic form in modeling toolkit and automatically gets the solution for you. Catalyst, which is for chemical reaction networks and automated discovery of chemical reactions. Right, so there's a lot of libraries in here, and I can't describe them all, but these are just some that people find interesting. Also, if you're interested in dynamic mode decomposition, or you want to know about how we do the sparse identification of the dynamical systems and sparse identification of neural networks, that is this data-driven diffeq library. So how do we get to this whole ecosystem, and where does it all come into play? Well, the core of this ecosystem is differential equations.jl. So what is that library? So it is MPI and GPU compatible, right? So you can make your state variables be, distributed arrays and that are talking with each other over MPI. You can put these distributed arrays on GPUs as well. You can mix it too. You can use multi GPUs and all that. So it is a large scale high performance differential equation solver with implicit methods, implicit explicit methods. So IMEX, multi rate solvers, symplectic solvers, exponential integrators. The whole list of all these different types of integrators are within this library, which I said, over 300 now. Um, there's adaptive methods for high order stochastic differential equations, which is quite unique. Um, stiff state dependent delay differential equation solvers with the discontinuity tracking. So all these kind of bells and whistles. And another bell and whistle here, which I'll explain a little bit more, is automated sparsity detection and optimization. So what we do to be able to build this ecosystem for scientific machine learning is we start with a differential equation solver that has all of these capabilities, and then what we do is we have these extension libraries that automatically compose with it, to be able to give it this neural network compatibility. Um, and this library has had years of refinements, right? So at this point, there's been around I think like 40 to 50 contributors who have kind of been active over the years on this library. And so if you're to time it against things like SciPy, MATLAB, or R, you see that's about like 50 times faster than SciPy, 50 times faster than MATLAB, 100 times faster than RSD solve. Even though these are calling optimized wrappers, because a lot of this actually has to do with the way we're optimizing the higher order function and directly recompiling differential equations within the solver itself and allowing for interprocedural optimizations. And so um, against these other high order languages, we're seeing orders of magnitude performance gains. But there's actually something else that you kind of see in the slide here, which is that the best performing method, even if you do it directly against C++ and Fortran methods, you see that the best performing methods also tend to be these pure Julian ones. And routinely, what you'll see is that the stiff ODE solvers and the non-stiff ODE solvers, but I'd like to highlight the stiff ones for people who are really deep in, because most real equations are stiff, right? The stiff ODE solvers tend to routinely outperform those of Sundial CVODE and the classic Fortran methods like Radow and LSODA. And we have, you can go to SciML benchmarks .jl and see benchmark after benchmark after benchmark. There are some cases in some places where a traditional method will outperform our new implementations. Like for example, if you go to really low error, Radow tends to have a very good scaling. But if you're in standard error regimes and for most equations, what you'll find is that things like RODOS5, these new Julia-based methods, tend to be the fastest stiff ODE solvers for a lot of these different cases. And so there is quite an advantage to using the differential equation software, even just for simulation of stiff systems. Um, and now the timing difference that you see against the other neural network compatible libraries is not small, right? Because what we're doing is we're starting from a ecosystem, which was it started from just being, high performance differential equation solving. And then what we did was we made sure that this neural network compatibility we made sure that the library was extended to have this capability instead of starting from scratch. So if you're to start from scratch instead, right? So for example, there's this torch diffeq library built in PyTorch, which first of all only has, a fifth order non-stiff ODE solver. It doesn't have all the bells and whistles. But even if you do a timing on, an ODE system of 3 ODEs, so Lorentz equation, Pleiades and body equation, some reaction diffusion discretizations, right? So if you look at ODEs from 3 to 700 or 800,000, you see that the closest it gets is that differential equations.jl is only 31 times faster than the TorchDiffEq library. But in the worst case scenarios, it ends up being that differential equations.jl is 6,000 or 8,000 times faster than these new differential equation solvers because they haven't had the years and years of optimization, right? So this is if you just kind of like take TensorFlow and use their differential equation solver, it uses a lot more function calls than it needs because it doesn't have all the bells and whistles and the time stepping routines. It doesn't have all the new methods and all that because it is kind of a really quickly ad hocly written, master students ODE solver. and it happens to be compatible with neural networks, which is why people like to use it, but it doesn't have all of the bells and whistles of like a fully formed differential equation solver library. And you see that in terms of the solving time. You see it in terms of the training time, where if you take their example problems from their documentation, you can train a neural ordinary differential equation in 300 seconds, but with DiffyQ Flux, you can train this in 3 seconds. Um, and if you look at this in terms of the SD solvers that have recently been put out in Torch SD as well, if you take the optimized code that that they use in their paper for their benchmarks against just pure Python code, if you just take that code and you just define the differential equations.jl SD, you see that you get about 100 times faster just by using this pure Julia library. So the performance difference against the other neural network embedded libraries is not necessarily small. And there's this other slide that I want to show in here. Um, so where does this neural network integration really come into play? And so the key to allowing neural networks in a way that is efficient is it comes into the way that you do the adjoint differential equation. So when you build these adjoint methods, so for example, in the adjoint of an ordinary differential equation, um, this adjoint of an ordinary differential equation, it has what's known as a vector Jacobian product in here. And this vector Jacobian product is something where you have the Jacobian adjoint times a vector. And if you're to do a numerical version of this library, what you do is you would calculate out you transpose it and multiply by the vector, and that's how you'd have to do this numerically. But it turns out that there is if you have n rows, that would be an O of n operation to be able to calculate this Jacobian. But it turns out that there's actually a trick you can make use of to turn this into an O of 1 operation, actually one function call. And is that if you push forward with the current value of u into the ODE right hand side f, and then you pull backwards with lambda in a reverse mode automatic differentiation system. So one reverse mode automatic differentiation call on the right hand side of the one reverse mode automatic differentiation call on the right hand side of the ODE function can actually give you this full Jacobian Jacobian transpose times vector product, and what would have been O of n operations if you're to use finite differencing or forward mode automatic differentiation. And so what we did inside of this this adjoint method, right? So if you use a differentiation call on the differential equation solver, it will automatically replace the reverse mode of the differential equation by solving an adjoint equation to be able to come up with the derivatives. And within this adjoint equation, it is using reverse mode automatic differentiation to accelerate the way that it's calculating the most expensive term of the adjoint equation. And it essentially gives you an O of 1 form that is a lot faster than traditional numerical ways of doing this. And there's a lot of different choices for how you can do this computation that are built in the library. Please ask questions on this portion if you're interested in more about it. But essentially, it is using a reverse mode AD trick to be able to really decrease the cost of adjoints. And so the reason why this new SciML architecture is really starting to be used, especially in this form, is because as you get to really large numbers of parameters, it very greatly decreases the computational cost. And so where you find this Julia ecosystem to have its benefit is the fact that there are previous libraries that have automated adjoints on time stepping. So sundials and new PETC's TS, right? These are libraries that have adjoint methods on there, right? So stabilized checkpointing and discrete sensitivity analysis on there. Our new library has 8 choices of this. So it has stabilized checkpointing, it has discrete sensitivity analysis, reversing adjoint. So it has all the methods it has all these other methods that the other libraries have, but also has the AD integration to be able to handle this term in a way that is O of 1 instead of O of n, which is not something that you could do with a purely numerical library. And it is something that you could do with like PyTorch, but again, these PyTorch libraries, they don't have MPI integration, they don't have the ability to handle stiffness or DAEs, they're fairly slow. They don't have event handling. They don't necessarily have good SDE libraries, and they don't have delay differential equations, right? So all of these all these extra equation forms, the handling of large scale equations, with the AD integration and stiffness handling are what we've been able to do. So in some senses, it's handling all of the aspects that you would need. Um, and there's always someone in the audience who wants to ask a question of whether it has the bell and whistle that they care about. So I like to have this slide that says, in 10 lines of code, here is the equation, which is, it's a neural ODE. So neural networks embedded into the ODE, which is doing batching on GPU. So the GPUs are used here with a high order implicit ODE solver. So a high order adaptive implicit ODE solver, but it also is a implicit explicit method with matrix-free Newton-Krylov and preconditioned GMRes and trained with checkpointed adjoints, right? So this probably hits one of those things that you would have cared about if you were going to ask a question of whether you can do X, Y, Z. Here's 10 lines of code that does exactly that, right? So a Jacobian-free Newton-Krylov with checkpointed adjoints and all that. Yeah, at this point with the library, it's fairly trivial. It's like 10 lines of code. You just tell it to do that method, right? On GPUs and with MPI and all that. If you want more information on using the library in that sense, you can check out this tutorial. So the second tutorial in the documentation differential equations is really one of the ones that I think has a lot of the key details for people who really solve really difficult equations. It showcases automated sparsity detection, preconditioned and Jacobian free Newton Krylov, matrix coloring, sparse and automatic differentiation, and symbolic Jacobian calculations on numerical code and all that to be able to do all these, optimizations on very stiff equations. So if you want to see a lot of this in action, check out that second tutorial. It shows up as the second part of that documentation. So what are some of the things that we have added to the differential equation library that allow it to do some very non-standard things? When we have this ability to be able to automatically offload computations to accelerators, so you can write a full CPU model, and you can turn on the automated accelerator, and what it'll do is it'll find portions of the solve, and it'll automatically throw them to the GPU when it understands that it's going to be accelerated. Yeah, so basically one of these libraries that we have is we're starting to make it so that way you can choose to do GPU integration if you want, but you can also say do the GPU integration automatically. So automatically send things to the accelerator card when it's a big enough operation to do that. So LU factorizations and matrix multiplications, make use of this automatically, and you can have a CPU based model, but when it hits the sparse LU factorization that shows up in the differential equation solver, you can automatically have that offload and accelerate by 10 times or 100 times, given your graphics card and how large of a problem that you have, by using this pirating of the operations. Another example that I like to show, it's kind of a cute example. You can do these biological models where you're changing, these biological models that people have originally thought you can never do with a differential equation solver. You can encode it. So here's an example of whenever you have a protein that gets to whenever you have a cell that gets to protein X, you can split that into two cells. And so you can represent this as here's one ordinary differential equation. When the differential equation hits 1, I have 2 ordinary differential equations instead of things changing size. And this is something that we can now do in this scientific machine learning form. So you can say, here's my ordinary differential equation. It's a linear ODE, but whenever I have any term hit 1, divide the ODE, create new ODEs, and so I'm dynamically changing the size of the ODE inside of a stiff ODE solver, and so this is kind of a complex model, right? Because whenever you have these hybrid events where whenever an event occurs, you're actually changing the amount of ODEs that you're solving. And so here's the number of ODEs over time, right? So the number of ODEs starts at 1, goes to 30 something. You can look at the amount of, the amount of protein in a given cell over time, which is just the amount of value, the value in protein 1, which goes up, it splits, and then it has a second split. Then all the other splits happen from other terms. Right, so this is a stiff equation, which is of changing size, which is also hybrid, which also can have learnable pieces of information in there. You can embed neural networks and learn missing physical terms inside of such a model as well. And I did want to point out that these 30 lines of code is the complete code for doing this kind of a model. So, how do we get the neural network integration into this library, right? So, how do we make it so that way we can get back propagation? Whenever you are doing adjoint methods, it is calling reverse mode AD, which is automatically doing back propagation whenever it sees the neural network. How do we make all these things automatically compose together? Instead of trying to do it by hand. So a lot of libraries have done before, right, is you kind of write down like, here's my domain specific library, and um, here's my domain specific library for this physical equation, and you write down the adjoint equation and things like that, right? How are we doing this in a way where we are automatically building adjoint equations in ways that are efficient? And also, whenever it sees a neural network, it replaces inside of the adjoint equation, it replaces things with back propagation in a way that is the most efficient. So how are we doing all this adjoint building on the fly? It all comes down to code generation. So it's all compiler based. And to really understand why everything is built in Julia here, I do want to showcase a little bit about the Julia compiler and how what some of its techniques are that we're using. And the general idea is that if I'm to look at an equation like 2x plus y squared, you can understand that as a mathematical equation, but it doesn't actually have a real backing, right? Because mathematically, it doesn't have a definition until I actually say that x is an integer and y is in the real numbers, right? And so, this is what we call a generic algorithm. So it's an algorithm without full specification of what the types are. And in order to know how actually what this algorithm means, you need to, impose a type on it. So here you can do something like say, um, make the type of these numbers be float 32 or float 64, and that instantiates a version of the differential equations, which are or of the function, which is then actually has a true meaning, right? And Julia does this by default. So if you write down an equation f of xy, you say that this is equal to 2x plus y squared. If you do the code LLVM on the version where you put in float 32s, and if you do the code LLVM, so if you look at the underlying assembly that's generated for float 64s, what you'll see is that you get different assembly for the different types, because this is not a single function. This is actually using what's known as multiple dispatch to be different assembly languages under the hood, which are optimized for the different forms. And so this is actually what people, this is the main reason why people know the Julia programming language. Right, so the Julia programming language, if you write code in it, even though it looks like kind of like MATLAB or Python, you end up with code that is as efficient as C or Fortran. And the reason is because of this, right? Because it's specializing on your types to build something that is, that is as efficient as the C code or the Fortran code that you would have built, right? So if you wrote a C code that has all of the type specifications in there, you compile it down, you check the assembly language, you check the native language here, you get exactly the same form. So this metaprogramming approach is how Julia gets its efficiency. But what we have done is we've used it as not just something for efficiency. I mean, we do use it for efficiency, but what we've also done with this is we've turned it into a method that we can use to be able to generate mathematical equations themselves. And one way to be able to see how you can do that is by understanding automatic differentiation through algebras. So for example, automatic differentiation, one way that you can start is you can say that it comes from complex, it starts from complex step differentiation, which is saying that the best way to be able to get your derivative is to not take a small step in the real dimension, but if you have a real valued function and a real valued input, you can take a step in the complex plane, and then you can take the imaginary number that comes out of that, and that's an approximation for the derivative. And you can show this with the Taylor series approximation. Any students in here, if you're curious about how this is done, I do have a lecture series about automatic differentiation, which will go into a lot more detail than this. Um, but what you can do is you can implement automatic differentiation as an algebraic change to any given piece of code. So you can say, I have a piece of code that works on numbers, but instead of working on numbers, instead use a dual number, which is a two-dimensional number, right? So complex numbers are a two-dimensional number. You can make this so that way their function doesn't have to be complex analytic by saying, here I have a two-dimensional number where I have epsilon as a domain specifier. So this is like, we have float 64s. This is a 128-bit number, where what my rule will be for deriving the what to do on this number type is that whenever you have epsilon squared, this is equal to 0, and you define f of x to be something where you have the chain rule applied. So we call this the value term or the primal term, and we call this the derivative term. And it turns out that with just these few rules, you can derive what your a lot of expressions would be. So you can derive a whole algebra on this, and you can redefine what plus means on this operation. You get the sum rule for the derivative. If you redefine what the product rule is using this term, you see that this is the product rule, and you can build a whole algebra around these dual numbers, and you can recompile your entire program so that way instead of doing standard arithmetic, it's doing dual number arithmetic, and that is one way to do forward mode AD. And you can do very similar tricks to be able to do reverse mode AD on arbitrary code. So you can then say, here's any code in the whole language, make it so that way I can automatically derive what the adjoint is for this code. And you can do all this you can derive specific equations for specific functions, and then you can use a compiler to be able to do this to change what your functions are and do a source to source change, source code changes on the functions to be able to build adjoint equations on the fly, even though you're in a dynamic programming language and writing things interactively in a REPL. And so this is how differential equations.jl is doing a lot of its adjoint building. While what I describe here is directly on forward mode, this is also done with reverse mode and the adjoint forms as well. So composing with machine learning is really just the latest part of the story, right? So I mean, here I showed that there's a lot that can happen with if you allow yourself to have neural numbers embedded with your differential equations, you can automatically discover equations. You can accelerate things, and all of this comes from making sure that adjoints are automatically constructed with the differential equation solver and stiffness. So that is a whole story in itself. But what I want to end with showing here is just different ways that this composability has been able to be used for solving different problems, right? To kind of show that these compiler tricks are actually able to be used throughout a lot of different mathematical problems that you might not have thought of as a compiler kind of problem. So here's an example where one thing that is very interesting about a real composable library is that you have users tell you about features of your library that you did not know about years in because the compiler actually generates new features. And so here's one example of that we found in 2017, where a user on the discourse forums actually posted, and this is how we figured out a new feature of the differential equation solver library. And they said, here I defined a measurements.jl, which is a new number type. I put it into differential equations.jl, and it just worked. And so therefore, we have a new feature. So what was this new feature that the user found that the compiler was automatically generating? They had done. If you have a number, x plus or minus y or a plus or minus b, you can think about that as being a normal approximation. And what you can do then, you can use a Taylor series expansion of a function, be able to figure out that if a is normally distributed and b is normally distributed, then f of a b, if it was normally distributed, what would its approximation be? And you can define what the variance covariance matrix would be and what the new mean would be, and use that to build a new approximation. So you can then build a number type that is pushing forward the uncertainty in terms of plus or minuses and automatically propagating uncertainty without doing random sampling. And so here's an example of equation solver. Here solver, we to use this algebra within it, and so we say the gravitational constant has, it's 9.79 plus or minus some uncertainty. The length of the pendulum has some uncertainty. Initial condition has some uncertainty. We define the pendulum equations, and we solve the differential equation. And what you could also do, since this is a pendulum, you write down the analytical solution, you plot the two, and what you see is that the solution automatically pushes through equations with these uncertainties, and the plot automatically adds these error bars to it as part of the way that the uncertainty library works. And so in one ODE solve, you have both the solution and the error bars, and it matches the analytical solution doing the numerical method and the analytical method. So it's hard to see that there's two solutions in here because they're exactly on top of each other, right? You get the same solution as the analytical solution to 6 digits of accuracy, and the error bars match to 6 digits of accuracy. Uncertainty quantification in a algebra, and then making it so that way the differential equation solver is compatible with all algebras, and just making it recompile on the fly with JIT compilation to this new sensitivity and or to this new uncertainty quantification. Another example of this is that, in Sobolev function space theory, you can represent L2 functions as vectors in L2 function space. So for example, you can use a Fourier decomposition, and you can say f of x as a function is just a vector given by the coefficients in the Fourier expansion, right? So you can always write down functions inside of function bases by their functional expansions. And this is a number in a vector space, right? So this is like, you can think about it as a, if you, this vector is a scale, this function is a scalar value inside of the L2 functions. And so in this representation, then we can define an algebra, right? We can multiply two functions, you can add two functions, and you can define this algebra on these vectors of the coefficients. And what you can, and by semigroup theory, an ODE defined on an ODE where your scalars are L2 functions is another representation of a partial differential equation, right? So computationally, we can use this to be able to be a new method for developing PDE solvers directly from ODE solvers. So here's one way to do that as a compilation trick. Use a fun, it's like an L2 function inside of a Chebyshev space, and it treats it like a number. So you can add two of these functions, you can multiply two of these functions. So what we do is we make one of these functions be the initial condition into the ODE solver. We say that the ODE is to take the second derivative in space of that scalar value, and then we solve the ODE defined by this scalar, where that scalar is a function, and the solution is the heat equation, right? So this is a way to be able to specify the heat equation as an ODE over function space, and then what you get out of this is that you get a adaptive space, adaptive time pseudo-spectral ODE solver, which is highly efficient, where no one actually has to write the code because it's all generated as part of this algebraic process. Um, so I don't think that there's another code out there which is, a fully generated adaptive space adaptive time method, right? Normally, if you're to do this, you'd actually have to write the code. But in this case, this is an adaptive ODE solver mixed with a adaptive approximation of functions in a function space. And when you put these two libraries together with the right compilation tricks, then it kind of just builds itself and it solves partial differential equations in this semigroup theory formulation. And so one of the last things that we've been looking at is what happens if you start to, how do we start to get the Modelica mixture in here? This which is to create, then you can start to get these tools or these like freebies for along with the modeling language without having to do any work. And this is a modeling toolkit, which is a modeling language for numerical Juliet programs. So what does that look like? Well, you can first think about it as being something like SymPy or SymEngine or Mathematica, right? So it's a full symbolic library. You can define equations inside of a matrix. You can simplify equations, right? And so in some sense, it is kind of like SymPy or SymEngine or Mathematica. It is a symbolic simplification rule library with a lot of symbolic tools that you have available. But what it can also specify is it can also specify things that you more think about as a high-level language, kind of like Modelica. So here, for example, is a symbolic specification of an ordinary differential equation, where what we think about is we can say like transformations of the ordinary differential equation or compiler passes on this representation. So here is a high-order ordinary differential equation. You can say do order lowering, and then you can say do Pantelidis algorithm or do BLT transformations, and then define the terms and solve the differential equation that it comes out of that. And so this is kind of like a deconstructed form of Modelica. Modelica has specific, it takes in your symbolic form and it does specific passes on it. In this form, there are actually more passes that you can do. Yeah, and you can reorder the passes. You can write new passes. You can do things where you say, take this ordinary differential equation, exponentiate my terms so that way all the terms have to be solving in a way that's always positive without numerical difficulties that can make it negative, and then do Pantele's algorithm. You could do all sorts of transformations on it in this exposed form. So it is both kind of like a SymPy SymEngine kind of library. We can also think about it as like an extended Modelica, which also handles more transformation passes, stochastic differential equations, partial differential equations, control systems, and a lot of other things. I will say that the modeling toolkit library is not completely done. We are looking to like really have a full Modelica replacement in like a year and a half, and we're working heavily with Hilding to make sure that we can import the Modelica standard library into this. There is a component-based system which I'm not going to show here as well. So one of the interesting things about the modeling toolkit is it can represent a lot of different numerically difficult mathematical problems like ODE systems, SDE systems, optimization systems, reaction systems, jump systems, PDE systems. So here, for example, is showing the physics-informed neural network solver library where the representation is symbolic. So you just symbolically write down, this is a heat equation. So dxx, dyy, it equals sine. You say, here's the neural network that I want to use to solve the differential equation, and here then it trains the neural network to be the solution of the differential equation, right? And so we have automated PDE solvers that we're building in neural network forms and in finite difference methods, and also finite element methods are one of the things that we're adding soon as well to this kind of symbolic form. So this is just kind of showing that it's a kind of general some kind of symbolic specification of differential equation with solvers in there. But here's where it starts to go beyond what you might have seen before, right? So what we could do is we can take fully numerical code, and since it actually since it has the same, since this symbolic language is the same language as Julia itself, we can take this numerical code. We can build symbolic variables, and we can put our symbolic variables into the numerical code and automatically translate it into symbolic code. And once we have the symbolic code, now it's in a declarative form, and we can do whatever we want with it. So we can automatically translate numerical codes into symbolic codes. And then what we can do is, for example, we can say, calculate the sparse Jacobian and give me what the analytical solution to the sparsity pattern and what the Jacobian terms are, right? And it'll spit out this. Also, what we do here is we say also automatically multi-thread it in a way that is using all the cores in my computer, or automatically find out how to distribute this across a cluster. And then here you can see the code that it generates, and it generates a code that is walking linearly through the non-zeros of the Jacobian, filling in the Jacobian pieces, spawning threads for these given areas. And so what a lot of the Julia Lab is working on right now is dynamic schedulers and ways to do this in very efficiently over clusters, so that way we can, you can take a numerical code that you've written, and we can automatically put into this declarative library and reformulate your code, so we can automatically give you back a parallel form of that code, or we can also derive Jacobians of that code, sparse Jacobians. So you give us a numerical code, and then we give you back an automatically parallelized version of the sparse calculation of your Jacobian, right? And so a lot of this is just occurring because of these same compiler techniques, right? It's treated as symbolic, it into symbolic and working with the compiler on your numerical objects, just similar to what we're doing with the machine learning integration, but here now for doing things that you would traditionally think of as like symbolic or Modelica like, but directly on code. And some recent features that aren't in the slides here that are very interesting is, for example, someone could give us a numerical specification of a DAE. We can automatically transform that into the symbolic version of the ordinary differential equation. We can check what the index is, and so then we could tell the user that we can't solve their ordinary differential equation because the numerical code that they wrote down is actually index 3 DAE. And then we can automatically translate this into the index 1 form, numerically solve it, and give back the user the solution to their numerical to what they've written down numerically, all transparently without them having to use the symbolic system by doing this index reduction on their original numerical code. And so what we've been able to show is that, and what this looks like is you define an ordinary differential equation in the standard way that you do in the differential equation library, and then you just call modeling toolkit ties. So this modeling toolkit ties, what it does is it takes this ODE function and the compiler looks at this function, reinterprets it back into the symbolic form, so then it can do this analysis. So here's like a fun example where someone has written down an ODE in a form that's very bad, right? Because it's allocating lots of small vectors, and so what we do is we don't tell the user that they're programming inefficiently. What we do is we just say, well, just use the tools, right? So they give us an ordinary differential equation, which is inefficient code. We tell them to automatically translate it into the symbolic version, and then we let the symbolic version build a new version of the ODE problem, which has a analytical Jacobian in there. And this is one way to get a 10 times acceleration on a stiff ordinary differential equation, where the user doesn't have to make sure that they write down fast code. The user doesn't have to make sure that they write down a Jacobian. All of that is actually done for free using these compiler tools on the symbolic form of the underlying equations. And so, for example, and this is quite general. So you can write down, for example, here is a discretization of a semi-linear partial differential equation, and we can use these compiler tools to automatically detect that this is the underlying sparsity pattern of your Jacobian, and then reduce the effort to solve this equation by 50 times. And this is actually one of the examples that's in the second tutorial of the differential equation solver library. So these days, a lot of people are not having to actually write down sparsity patterns to get the full efficiency, right? Sparsity patterns and all these kind of things can come for free from automated program analysis. And other tools that we have that are kind of related to this is that we can take these small differential equations and we can re-index them in a way that is more efficient on GPUs. So even though it's a very small problem, like solve 3 ODEs in a few milliseconds, if you want to solve, 10,000 trajectories of these really small ODEs, we can re-index your problem such that it becomes a GPU problem. So here is actually the full code difference between the GPU version and the multi-threaded version. Actually, this change is no longer required. Now, actually, it only requires doing this change from ensemble threads to ensemble GPU array. And what will happen under the hood is we generate a new version of your ODE, which is more compatible with GPUs, right? A similar compiler trick. And if you're solving thousands and thousands of equations, then you can solve these really small differential equations about 175x faster. Transformation to a GPU-based code for pharmaceutical company, because they have to do a lot of these 15 to 50 stiff ordinary differential equations, doing thousands and thousands of trajectories for global optimization and such. And we now have this in a way such that you write down your differential equations, and it will do the automatic transformations for you. And so what we really get in the end is we have a composable software tool that allows for, integration with machine learning, but then also a lot of other problems like building PDE solvers, getting adjoint equations, doing uncertainty quantification, automatically parallelizing code. A lot of these things come for free because these are all just different ways to think about composing software with compiler types of optimizations and compiler types of code transformations to be able to give you GPU compatible, machine learning compatible, et cetera, stiff differential equation solvers. So you can do things like mixed delays and stiffness and neural networks and differential algebraic equations and get optimized speed like what would happen if you were to actually have handwritten a equation and the adjoints for a given equation. So what we found is that simulations that really take months by hand, we can now start to generate with 30 lines of code, and we're not generating the just the simple ODE solver version. We're generating the version that has reverse mode embedded O of 1 adjoints with in there automatic building informations. And so that's really the key here, right? That really, in the end, the scientific machine learning organization is all about a whole bunch of pieces that compose together, and you can start putting all of these compiler transformations on top of each other to get quite complex applications and do automated discovery or just get faster differential equation solving in the end. So yeah, so thank you. That's like a high level overview of what we built, and that's differential equations in 2021. A lot of what we'll be doing is working on modeling toolkit to be able to do a lot more symbolic tools and more acceleration and more distributed parallelism.
So thank you very much. Very interesting to me, and I hope also to the audience. I still see there are a lot of attendees. So maybe we have time for a couple of 2 or 3 or 4 or 5 questions. If anyone wants to sort of use the hand sign, I can give the word to them. Raise your hand. I can start with just what is nice is that this fits into the Julia language itself, which is very similar to MATLAB and Python and R and so on, and has very good packages in many other fields. So can you say a little bit about how this integrates with, is it possible to integrate it with Python, for example?
Yeah. So there are some things that we aren't able to do with the Python integration, right? Because some of these things are built out off of compiler tools. And in order to do the compiler type analysis, we do need to know the symbolic form, and that's all able to be done on Julia. But if you don't use the compiler-based tool, so if you're just like, I want to use the differential equation solver and some of the adjoints that don't require such integration with the compiler, you can directly use those from Python. So we actually have a library, which is let me just kind of pull it up. This is the magic of doing online talks, right? That you can just kind of pull everything up. And so here's diffqpy, which is the ability to solve the equations in Julia with a feedback. And so this is still kind of a work in progress. You know, it handles ODEs, SDEs, random differential equations, differential algebraic equations, and delay differential equations. It doesn't have all the speed yet, and there are some things that we're still working out. The one that would actually point to that is more complete, there's a blog post on the R version, because we've actually been able to show how to make some of the compiler tools work on the R version. And so we can directly take code written in the R language and automatically recompile that to GPUs. So we have this form where you can say, here's the differential equation in R, but use the JIT optimize ODE function, which is essentially turning it into a modeling toolkit code and rewriting the R code as a Julia code, and then solve this using the diffq GPU that I mentioned. And so that gives you about a 330 times speed up over the DE solve library of Julia, or of R, just by doing both the JIT compilation of the R code and the GPU acceleration. We haven't been able to do all of that on Python yet, but this is one of the directions that we're going in, 2021.
Okay, interesting. So, but if you wanted to make a very simple system, if you have both Python and Julia installed at the same time, you could, and if you're very good at creating a user interface in Python, which calls Julia, that should work fine.
Yeah, exactly. Actually, one of the big battery models, so PyBAM, is actually one of the big users of PyJulia now. So PyBAM, you can see that there actually are packages which are already built in Python that GitHub does pick up that are using diffqpy in the background. One of these is PyBAM, which is another num-focused organization, a big battery model, and it's using Julia for it's using Python to build differential equations and using this diffqpy to then be able to solve the resulting differential equations, where it's defining the codes in Julia, and it's using that to be able to accelerate what they had before. So you can use this in that direction. You can also call Python code from Julia within differential equation solves, and you can mix R, Python, Julia together. I used to have this slide in there, which is 5 lines of code, which is solving an equation in Julia where the differential equation is defined in Python. It's plotted in R, and the data that we're fitting comes from MATLAB. And so it's Julia, Python, R, MATLAB, and there's a C code in there and a Fortran code in there. And in 5 lines of code, you can do model fitting with all the languages together. So yeah, you can do these crazy examples. Interop isn't too difficult here.
Yeah, well, one question, if I don't see anyone others yet, so I continue to ask. I understand, well, you're talking with Hilding Elmqvist, which some of us know as one of the founders of the Modelica language and also the original developer of Daimola. And of course, Modelica is very good with library support. You can build libraries and then you can connect things. And I would assume that you have similar ideas with the modeling toolkit.
Mm-hmm.
So and as I understand, you can also mix and match different types of differential equations like PDEs and ODEs and DAEs and stochastic differential equations.
Mm-hmm. Yeah, so I'm not going to go over the full details of what we have going on here. This is a larger project which we're doing in collaboration with Julia Computing. So we wanted more manpower to really be able to get up to speed and surpass Daimola. And so we built it. So we got a few RPE grants to be able to get this team of around like 20 programmers working on this modeling toolkit now. And so it has a whole. Let me see if there's a slide in here for that. But essentially, it has a whole. It has a whole Modelica-based a system for doing component-based modeling. We have tests against Daimola. We're able to outperform it in the building model simulations. So we have areas are being built out already, like refrigerant properties for building simulation, and showing that it can outperform Modelica by using two ways. So you can get 20 times faster by using embedded neural circuits. So you can transform components into smaller versions with neural networks, and then you can recompose these surrogates inside of there. There's a recent paper that we put out on that if you're interested in the surrogatization. But another part of this is that we have new differential equation solvers which are able to handle these discontinuities in a way that's much faster than for example, the Daimola version of Dassel or sundials. And we're making use of these inside of the new component-based library, and that's how we're able to showcase, being 10 times or 20 times faster than Daimola. So this is still an ongoing project, and there's a lot of tools which are proprietary to Julia Computing right now. We're going to have a product release around those. And so what's happening with Modeling Toolkit is that we are working with Holding and with Julia Computing. The core of Modeling Toolkit is free and open source, but there's going to be these add-on libraries which are proprietary, which kind of give more differential equation solvers or more transformation techniques. And we're working with Holding to make sure that you can automatically transform from Modelica language to Modeling Toolkit by using Modia as a middle ground, right? Because Modia can read in the Modelica standard library, and you can transform Modia to Modeling Toolkit. And then we're also making sure that you can have other integrations. So one of the things that we're building this month, actually it's kind of due to be released sometime in late November, is the ability to output FMUs and FMIs. And so I think the first product that you'll see around this will be we can take in FMIs, we can automatically transform them into surrogate versions, and we can build new FMIs there, like the 10 times to 100 times faster version, and those will be compatible with Daimola. And so so we're getting the ability to read in Modelica standard library and have a component-based system and output FMIs in a similar fashion that is compatible with the existing Modelica tools. So we're getting there. We don't have all of that yet, but this is one of the ongoing projects that is going on behind the scenes. Partially commercial, but also with an open core, so people can use this open source, but also get add-ons for extra speed.
Sounds interesting. I have one more question, and then I will stop. And then you mentioned composability and the possibility to integrate different tools. One problem that is of interest to me and probably others is optimization. And you have different optimization initiatives in Julia. One is called Jump, which is more like a language. But I also understand, I think I've seen that you also plan to develop or include optimization tools as part of SciML. Can you comment a little bit on the possibilities there?
Yeah. So one of the things that we found, there's kind of a difference between Jump and what's been going on in the nonlinear world, right? So Jump is a really great language for linear programming, quadratic programming, not mixed integer linear programming, like those kind of things that you have, very structured form. Jump really handles them well, right? So Jump is probably the best modeling language for those types of equations. Where Jump hasn't really traditionally done well is in the nonlinear forms, right? And so what we have with Modeling Toolkit now, so we have two projects that are going on in this area. They're not quite complete, but essentially what we needed inside of our new physics-informed neural networks and DiffyQ Flux libraries is we needed ways to be able to integrate a lot of these different, nonlinear optimization libraries. And so what we started to build was this galactic optim, which is essentially it brings together all of the global optimization and local optimization libraries into one package, which is why we call it galactic. It's more than global. And so you can, it's not fully documented yet, but this is a project to kind of watch. It basically has 10 underlying differential optimization libraries that can call, and automatically integrates with automatic differentiation for defining the derivatives and such. And one of the things that it does is it also has auto modeling toolkit. So if you give it a function, it can out with the tool. So so to be able to do some extra accelerations. And so what this can do is it can automatically figure out what the symbolic form would be from the numerical code and then ship that off to iPopt. I mean, so this is still kind of in development, but but it is part of what we're working on. So there's a nonlinear, there's an optimization system in modeling toolkit, kind of like, you have ODE system, which is like Modelica like. You have nonlinear system, which you can kind of think of as like steady state Modelica modeling. You have optimization system, which is like kind of like Jump for nonlinear programming, but with automated with automating some of the symbolic tools, and then we're building an optimization library that can use this symbolic backend with it. Not all of this is done right now, but this is part of this 1-year roadmap. Right now, what you can do with this is you can kind of call any Julia-based optimizer, and you can use the automatic differentiation. So we actually use this we're starting to use this in our tutorials for the scientific machine learning tools, because it's really nice to be able to switch between BFGS and Atom, which is usually used in neural networks, right? So we have neural networks inside of differential equations. You can use both the optimizers from the neural network library and from traditional scientific computing libraries, just switch between them. But now what we're really finishing with this library is this automated symbolic version of it. So that way it's kind of like Jump that acts directly on numerical code.
Good. Other questions? Please feel free to use the chance.